Standard physics models often begin with a specific set of givens, assuming metric space, momentum, and discrete particles exist as primitives, ready to be measured. Within this framework, phase serves a descriptive role. It identifies a position in an oscillatory cycle or provides a complex angle for a gauge transformation. Philip Lillian's phase mathematics proposes a reversal of this hierarchy. Phase functions as the first differentiable orientation of an underlying invariant coherence. This comparison highlights a shift in perspective. The left side maps phase as a descriptor of existing waves and state spaces. The right side illustrates the geometry of phase mathematics, where phase takes a generative role. In this domain, phase relations produce structural form. This framework reinterprets the physical world. It views reality as an unbroken unity becoming relationally expressible through phase. Coherence becomes relational without ceasing to be coherent. Multiplicity emerges through differentiation within the whole. We can examine this through a generative calculus that derives complex structure from pure unity, maintaining the integrity of the source throughout the process. With phase established as a generative primary, metric space ceases to be a valid starting point. We must derive the universe from its true origin. This diagram maps the foundational cascade. It illustrates a strict sequence of logical prerequisites required for structure to emerge, representing an order of dependency. We begin at the far left, with the primitive source. This origin point is coherence, denoted by C. Coherence is the source condition, an invariant relational unity existing prior to any differentiation. Here, coherence takes the first step towards physical reality by gaining an internal orientation. This is phase, denoted by phi. It introduces directionality while maintaining underlying unity. Moving right, we see the result of multiple orientations emerging within that same whole. This creates phase difference. By establishing distinct orientations, phase difference introduces betweenness, the first condition of relation. Under this model, difference begins as an internal phase relation. This distinguishes it from theories that assume spatial distance between already separated objects. This approach maintains the integrity of the whole. By starting with coherence, we avoid the logical gap created when models attempt to bridge the distance between independent fragmented particles. Phase mathematics establishes that relation precedes the existence of physical objects. Once phase differences exist within a shared coherence, those orientations interact. They intersect, amplify, and synchronize with one another. This active interaction is defined as resonance. Resonance expresses coherence in a relationally active state. This graphic illustrates the threshold of stabilization, the point where active wave interactions bind into persistent realities. On the left, we see resonance in an unstable state, manifesting as fluctuation or turbulence. The geometric star on the right represents stabilized structure, denoted by S. A structure forms when a resonance relation preserves enough coherence to persist through transformation. This suggests that particles, objects, and even physical laws are derived stabilizations of underlying resonance. Matter is understood here as a specific resonance relation that has achieved closure and stability. The theoretical ontology transitions into a formal mathematics through a nested operational calculus. This diagram illustrates the equation of emergence, mapping philosophical concepts to specific mathematical operations. Tracing the vertical lines shows how the foundational cascade dictates the structure of the calculus. 3 primitive tools execute this calculus. The operator triad. The coherence operator preserves invariant unity, ensuring identity is maintained during change. The phase shift operator introduces difference, enabling transformation. The resonance operator generates the interaction matrix between those differentiated phase states. These operators are strictly non-commutative, meaning the sequence of operations determines the resulting form. As the flowchart shows, shifting phase and then applying resonance yields a different structural stabilization than applying resonance and then shifting phase. These operations occur within generative phase space. Unlike classical phase space, which maps variables on an existing grid, phase space precedes metric spatiality. Distance and time emerge as derived measures of the ordered phase transitions occurring within phase space. We can test this calculus by seeing if it successfully recovers the standard concepts of mathematics and physics. Familiar mathematical categories are revealed as stabilized phase relations. Number is recovered as a stabilized coherence relation, capable of repeatable distinction. Equality is reinterpreted as a limiting case of exact phase equivalence, where coherence is preserved across a transformation. The phase lens reinterprets physical phenomena through the same grammar. Gauge fields are understood as local stabilizers of phase coherence. Particles appear as localized resonance closures, sustained within a coherent field. Phase mathematics discloses the generative engine running beneath standard physical models. Unity and multiplicity are seen here not as opposites, but as different phases of the exact same unbroken reality. By treating phase as an ontological primary, we possess a calculus where the emergence of the universe requires only orientation.